Hello, ladies and gentlemen. We're going to do 6.1 today. We're going to be talking about slope fields and differential equations. Our objectives are that we're going to generate slope fields, find particular solutions to differential equations, use slope fields to approximate, there's an and in there, and use slope fields to approximate solutions of the differential equations. So I wrote down some thoughts as I did a little bit of research about the differential equations and slope fields. The first one would be that slope fields can be used to visualize the flow of the solution curves of the corresponding differential equation. So at every point of the solution curve, the curve will have the tangent slope indicated on the slope field. So just to kind of illustrate that, if I drew a little curve and I generated a slope field of that curve, at every point along the curve, the slope field would show what the slopes are at that particular point, right? So if this was, I'll just call it point 1, and this is point 1, that could potentially be the slope at that point. So the slope field is just a diagram of all of the different slopes of the original curve. All right, when we are solving differential equations, which that's what DE means, the slope field can be verified to show that the explicit solutions match the graphical solutions. All right, so a couple of things that you need to remember from the last time that we did slope fields. A derivative derivatives create a family of curves. And we talked about this kind of in length last year, but if I differentiate a particular function, or I integrate a function, the general solution would be that I would get the antiderivative plus c. And remember, this is just a vertical translation, and so I can take the derivative of the integration, or I can integrate, just kind of depends on what the problem is saying, but it generates some solutions that have plus c because this is a general integration, and I don't have any integrand limits. So these are just some vertical translations that create the family of curves. All right, so now let's talk about generating a slope field. And if you'll remember from Calc AB, oftentimes the way this presents itself on an exam is that they will give you a function and then they will ask you to generate the slope field, right? And typically what happens is they don't give you a ton of points because it becomes super tedious. So let's say they gave you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, plus those points on the axes. So, and then you would generate whatever the slopes are at those individual points along the graph, showing your horizontal and vertical slopes as well. All right. So typically what happens is I have a differential equation, maybe this one. So this is my differential equation. And notice that when we do these problems, depending on the notation that you like to use, this could also be represented as negative, or y prime is a negative x over y. I think this notation is handy because if you remember, if I'm going to solve a differential equation, I'm going to cross multiply and take him over there, and then I'm going to take this guy over here. But if I am managing a different portion of the slope field problem, this notation is handy. So it kind of just depends on which portion of the process you are doing as to which notation is helpful. Alrighty, just a couple of things to remember also as we do this. Remember that dy dx is the slope of your tangent line, and we know this is true, but sometimes it doesn't hurt to restate the obvious, okay, to a curve at any given point. Okay, so what I'm doing is I'm creating a graph or a picture of all of the different slopes, the dy dx's, of the tangents to my particular curve. Alrighty, so let's just um, do an example from the one that I just had, do it in a different color. So let's say that I have dy dx, which is the example I just wrote down, and I want to go ahead and generate that slope field. And I'm not going to do it for a ton of values, but for a few. Alrighty. So what I'm going to do is I'm going to draw a grid. And I'm just going to put a few points on here because we don't want to get too crazy. So this is 1 and 2, -1, -2, -1, -2, 1, and 2. And I'm going to evaluate, and I'm going to put a little blue dot so we know where our slopes are supposed to go. There, and there, there, and there. My numbers are in the way. Oh, well. So these are going to be all the different locations that we would actually try to come up with the slope. Alrighty. You can manage this information in any way that makes your brain happy. You can put it in a table. So you could organize your information as x, and then I would have my y, and then I would have my dy dx. Or you can just kind of do the math. If it's a super simple equation, you can just do the math and not have to think about it too much. But I'm going to go ahead and put them in our little table just to manage a few. So I'm going to start on, actually I'm just going to start at the origin. So if I do the point 0, 0, and I substitute it in here, I'm going to write that the world explodes. And that would just be a really sad day. So the world is going to explode because it can't divide by 0. All right, maybe if I scoot it over, I won't have quite so much glare. And then if I go to the point 0, 1, when x is 0, notice that if x is 0, I'm going to get a 0. And remember, a slope that is 0 means I have a horizontal line. So at the point 0, 1, I would draw my little horizontal line. I don't know if you can tell that I'll do red. Maybe that'll show up better than purple. Alrighty, so then let's say I chose the point 0, 2. And if I go to 0, 2, okay, again, my slope is going to be horizontal. And so I would have a horizontal line here. And then if I did the same thing down here and down here, I would have horizontal slopes all along the x-axis, okay? If I look at some points along the y-axis, so maybe I look at, I'm sorry, these are the y-axis, and now I'm going to look at the x-axis. It's been a long weekend. Alrighty, so if I look at the point 1, 0, well, notice that I would get a -1 over 0, which is undefined. And yes, the world would explode. But what it also means is, since the slope is undefined, I also have a vertical segment. And I could also do that right there. So I'm going to put a vertical piece here. And I just did the point 1, 0, so I'm going to put a vertical piece. And if you'll notice, if all of my things are there, then I would have vertical components all along. Alrighty, and I'm not going to do all of them, but I'll just do a couple more. So let's say I do the point -2 and 2, which would be this one up here on the top left. Well, a negative and a negative is a positive, so it's going to be a +2 over 2, which is 1, which means that slope's going to go that way. And then if I move down to this point, when I do a -2 and then I do a +1, that means I'm going to have a 2 divided by a 1, which is 2. And this guy's going to be, instead of being at a 45-degree angle, he's going to be a little bit steeper. So you just have to show, and that's why it's really good to show your work, because sometimes it's hard to differentiate between a slope of 1 and a slope of 2. Well, if I proceeded to do this all the way around, you would end up with your slope field looking something like this. Here, oops, and here, and here, 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 and here. So it's kind of cool looking. Ooh, I missed one. And I would be much more careful, and I would show my work so that I could actually generate a polite field. You do need to be careful when you are drawing your slope field to try and differentiate between a slope that's 1, a slope that's 1/2, and a slope that's 2. So just thinking about the angle that those little slope field lines are going to take off at. Alrighty. Let's say I want to go the opposite direction, and I want to be given a slope field. These are often multiple choice questions. So if I'm given a slope field, and then I want to know which one it potentially matches, well, then what I can do is I would be given, like, maybe A is dy, dx is blah, blah. Isn't that lovely? And maybe B is dy over dx is blah, bleh. Isn't that just highly technical math language? Then I would choose a couple of points. I would not just check one. I would check multiple points, substitute them into the equations that they give you, and see which one generates the equivalent looking slope to the slope field. So you do just have to do kind of a trial and error, check points to make sure that you can find the one that actually works. Alrighty, another note that I need to give you, just as we remember this process, a function y is equal to f of x is a solution of a, I'm going to turn that die off and maybe the glare won't be as bad, of a differential solution. Okay, all right, I'm going to turn that one on, turn that one off. Maybe that'll make it better. Oop, I think I got it. If the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. Whew, that's a lot of writing. Alrighty, so now let's do some applications because I think that might help to set these concepts in stone. So we're going to be given, notice the lovely Christmas colors, the differential equation xy prime minus 2y equals x to the third e to the x. And the directions are going to say determine whether, and I don't know if you guys can hear it in the background, but it sounds like a hurricane out here in Donny Park. So it is quite crazy outside today. Is a potential solution of the differential equation. Alright, so basically what we're trying to do is we're going to take a function, and I'm going to have two different scenarios. So we're going to do an A part and a B part, where we decide if that graph, that f of x, is a solution of the differential equation. So the first one, we're going to be given that y is equal to x cubed, and I want to know if this differential equation, if this is a solution of the differential equation. So the first thing that I'm going to do is I'm going to take the derivative, and I get 3x squared. Well, now I can substitute these two things back into the differential equation that I was given. So if I do that, I'm going to have x times y prime, which is 3x squared, minus the 2 times y, which is x to the third. And I want to know, does that equal x to the third e to the x? That's an x. That's a pathetic looking x. Sorry. So then if I simplify my math, I get 3x cubed minus 2x cubed, and I'm still trying to decide if that equals x to the third e to the x. Obviously it doesn't, but if we just finish the math, I'm going to get 1x cubed. It does not equal x to the third e to the x. So y is equal to x cubed is not a potential solution of this differential equation. Okay? And I'm going to rewrite my differential equation so you can see it, since I'm going to another page. And I had xy prime minus 2y is x cubed e to the x. So for my second example, B, we're going to be given y is equal to x squared times 2 plus e to the x, okay? And that one actually looks like it could potentially be a solution of the differential equation because I have some e's in there and the other one had none. But before I take the derivative, I'm going to expand. So this is 2x squared plus x squared e to the x. Well, just like in the last problem, I need to take the derivative first. So the derivative of 2x squared, and I'm just looking at my math. I know what I did. Did I do that? Sorry, I'm just looking at my math. I think I forgot a term when I did my math. Sad day. All right, so when I take my derivative, I'm going to get 4x, and then this is the product rule. So the first term times the derivative of the second, e to the x, plus the second term, e to the x, times the derivative of the first, 2x. Okay? Did I get that? I guess I just did it in a different order. That's just weird. So this is my derivative. So now what I'm going to do is I'm going to substitute my y and my y prime into this and see if it simplifies to give me that. It doesn't look promising, but let's stick with it and see what we get. So now I have x, y prime is going to be 4x plus x squared e to the x. And I'm going to rearrange this one just a tad. And then I have minus 2 times y. Well, my y was x squared. I'm going to do my expanded version plus x squared e to the x. And I want to know, does that equal x cubed e to the x? Okay, which goes to show, since I had a little bit of confusion, that your math can be done so many different ways. It just depends on the approach that you take as long as it's legal. So before I do anything else, I'm going to simplify all this yucky stuff. So I have 4x squared plus x cubed e to the x plus 2x squared e to the x minus 4x squared, well that was polite, minus 2x squared e to the x, that's also polite, still trying to show if that equals x to the third e to the x. Well, these two guys cancel, and these two guys cancel, so I get x to the third e to the x is equal to x to the third e to the x. Well, there you go. Ta-da! So we showed that this equation for y is a potential solution for the differential equation because I got the right answer. Alrighty, so now let's do another example. And it says use integration to find a general solution. We talked about this at the beginning of the video, but that means that I'm going to have an indefinite integral, and when I integrate, I'm going to get a c of the differential equation, and it's going to be dy dx is equal to 2x cubed minus 3x. All right, so since I'm going to integrate to find a general solution, the first thing that I need to do is make all of my x's be on one side and all my y's be on the same side, which, by the way, is called separation of variables. It sounds like it's really fancy, but we do it all the time. We just collect all the y things and collect all the x things. So I'm going to say that dy is equal to, parentheses are nice, 3x dx. Well, if I'm trying to find a general solution, that means I'm trying to find y. Well, the opposite of the derivative is the integral, so I'm going to take the integral of both sides, which is pretty easy. When I integrate dy, I get y, and then I'm going to have 2x to the fourth divided by 4 minus 3x to the second divided by 2 plus c. Don't ever forget that little guy because he is just the end all to be all. Clean this up just a little bit, and I would write general solution just to make sure that there's no confusion about what I had done. Y is equal to 1/2 x to the fourth minus 3/2 x squared plus c. So that was actually fairly straightforward. example that I have is a wee bit more complicated. So I'm going to go to the top of a new page. Sorry, I have a little bit of a cold, so I sound a little bit like a frog. This one says, verify that the general solution satisfies, oops, can't spell, must be the wind, satisfies the differential equation, then find the particular solution that satisfies, that's a lot of writing, the initial condition. All right, so before we go through the rest of this problem and actually tell you the equations that we're trying to do math on, I want to point out the difference. A general solution, when we're talking about differential equations, means that I'm going to get an expression plus c. A particular solution means that I am going to solve for c and write a very specific equation for y. Alrighty, so you just need to make sure that you remember the difference between those two types of equations. Alright, so in this equation, I switched pens, but I guess I'll just stay with it. The general equation is going to be 3x squared plus 2y squared equals c. And then my differential equation is going to be 3x plus 2y prime equals 0. And my initial condition is going to be y is equal to 3 and x is equal to 1, which is just the 0.13. Okay, so however you choose to write that. So the first thing that I want to do is take the derivative of the general. So I'm going to take the derivative of the general equation. So 3x squared, the derivative is going to become 6x to the first. And then I'm going to have plus 4y dy dx, because remember it's implicit differentiation. Anytime I differentiate a y thing, I generate a dy dx, since I'm taking the derivative with respect to x. And then the derivative of a constant is 0, okay? And then I'm going to rewrite this as 6x plus 4y prime is equal to 0. But what I'm trying to do is show that the differential equation is equal to this. I'm close, so I'm going to factor out a 2, and I get 3x plus 2y prime is 0. Divide both sides by 2, and I get 3x plus 2y prime is 0. And this is my differential equation, and it is now verified. Ta-da! So far, so good. All right, so now I'm going to find my particular solution. And remember, I've been given the point 1, 3. So what I'm going to do is I'm going to take my general equation, which is here, and I'm going to solve for c. Alrighty, so I'm going to write 3 times x squared plus 2y squared is c. C is what we're trying to solve for. So I'm going to do 3 times 1 squared plus 2 times 9 is equal to c. I'm going to solve for c. So c is equal to 3 plus 18, which is 21. So then my particular solution is going to be 3x squared plus 2y squared is equal to 21. Alrighty? Is that pretty good? That was pretty easy. And then I don't think that's anything too crazy. All right, that is it for today. Not too terribly long. I hope you enjoy the rest of your Sunday, and I will see you tomorrow.